Next, we'll derive MLE for categorical models. Let's say that we have D classes indexed by 1 through D. The categorical variable X uses one-hot encoding to represent a class. X is a D-dimensional vector, and each element X sub k is either 0 or 1. To represent the case class, only the case element in X is 1 and the rest is 0. The categorical distribution uses D parameters, theta sub 1 through theta sub D, where theta sub k is the probability of the case class. Note that the probability must sum to 1. We can write the model density P sub theta as the multiplication of D terms. In the case term, if X sub k equals 1 and this term equals theta sub k, if X sub k equals 0 and this term equals 1. Because only one element in X is 1, X selects one and only one parameter as the probability of X. Taking log converts multiplication into addition, and in the log probability, each additive term is X sub k times log theta sub k, given k from 1 to D. To model the data distribution, we can take independent samples and index each data point by I. For maximal likelihood estimation, we define the loss as the average negative log likelihood. Using the definition of categorical distribution, we can write this loss in this way and switch the order of summation to first sum over I and then sum over k. We can take log theta sub k out of the inner summation and reorganize this equation. Take a close look at this summation. X sub k equals 1 if xi belongs to the case class, or otherwise x sub k equals 0. So this summation simply counts the number of times the training data belongs to the case class. We can denote this count as n sub k and simplify the loss function in this final form. Next, we want to optimize the parameters theta sub 1 through theta sub d to minimize the MLE loss function, subject to a constraint that the sum of all parameters equals 1. We can include this constraint as an additional term in the combined loss function, weighted by the Lagrange multiplier lambda. We can calculate the derivative of the combined loss with respect to each parameter theta sub k, setting the derivative equals 1 given all k's. We can estimate the optimal parameter theta sub k as n sub k over n times lambda. Because theta sub k must sum to 1, so lambda must equals 1. The optimal parameter theta sub k equals n sub k over n, which is the fraction of the training data belonging to the case class.